Hello everyone, so in this section we want to talk about the method of partial fractions to integrate functions. So often this is used for rational functions because it takes something that looks kind of difficult to integrate and turns it into something, into multiple pieces that are each easier to integrate. So you can kind of think of it as like a divide and conquer approach. So the idea is to decompose rational expressions into simpler rational expressions that are easier to rational expressions, let's say with easier antiderivatives. And the method for doing this is purely algebraic, so let me just show you how we might do something like that. Example. So let's consider the expression or the rational function 3x over x squared plus 2x minus 8. Now, whenever you have rational expressions, oftentimes it's a good idea to just factor whatever you can, because that might allow you to rewrite things. So the bottom can be factored here. We can factor that as x plus 4 times x minus 2. And again, you can kind of think of that as a common denominator. So maybe we can rewrite this in such a way that we can write it in terms of some rational function over x plus 4 plus another rational function over x minus 2. And I'm going to show you how to do that. So let's rewrite. Our goal is to rewrite as some a over x minus 2 plus some b over x plus 4. If we can do that, then we've kind of achieved our goal. So this will be known as the partial fractions decomposition of that rational expression. So let's see how we do that. So if we go ahead and we take on the one hand, we have 3x over x plus 4 times x minus 2. That will equal a over x minus 2 plus b over x plus 4. Now, if we clear the denominators by multiplying both sides by x plus 4 times x minus 2, on the left we'll have 3x, and on the right-hand side we'll have the x minus 2 will cancel, and I'll be left with an x plus 4. And then for the second term, the x plus 4 will cancel, and I'll be left with b times x minus 2. And again, this is multiplying both sides by x plus 4 times x minus 2. We just multiplied both sides by that polynomial and canceled out the factors where appropriate. So essentially what this leaves us with is two equations, right? Because essentially polynomials are only equal if the coefficients of each degree term are equal. So on the one hand, we have 3x equals, we're going to have an ax plus a bx, and then we're also going to have a 4a minus a 2b. So we can separate this into two equations. We know 3 has to equal a plus b. So this is equating coefficients of x. And we also have the equation 0 equals 4a minus 2b. And this is equating constant terms on both sides. So now we have a system of equations right here, and you can solve that with whatever method you prefer. Substitution looks pretty easy here because in the second equation, we'll quickly see that 2b equals 4a. So dividing by 2, we get b is equal to 2a. And then we can substitute that into the top equation, and we get 3 is equal to a plus 2a. So that means a is equal to 1, and b is twice a, so b is equal to 2. So that tells us that our original rational expression, which was 3x over x plus 4 times x minus 2, can actually be rewritten as 1 over x minus 2 plus 2 over x plus 4. And we could see why that's useful in an integration example. Why would that be? Well, let's just go ahead. So that's essentially the end of this example, but let's just note that this would allow us to integrate so this decomposition would allow us to find the antiderivative of the function. So the integral of 3x over x plus 4 times x minus 2 would be the same thing as the integral of 1 over x minus 2 plus the integral of 2 over x plus 4. And those substitutions are very easy. If you let u equal x minus 2, du is the exact same thing as dx. So the substitution isn't contributing anything that's going to change the constant that you're multiplying by. So these would just become essentially the natural log of the absolute value of x minus 2 plus 2 times the natural log of the absolute value of x plus 4 plus a constant of integration. And that would be it for actually taking this partial fractions decomposition and finding the indefinite integral. Let's go ahead and continue by looking at a variety of examples. You kind of have to remember some properties about polynomials to understand what's going to happen for when the degrees differ by a bit, but other than that, it's really just applying this algebraic technique. So let's say we want to evaluate the following integrals. So let's go ahead and start with one kind of similar to what we just did, nothing too tricky. Let's say we're looking at the integral of 6 over x squared minus 1. So what we want to do is we want to first do the partial fractions decomposition. So we're going to note that this is the same as the integral of 6 over x plus 1 times x minus 1. So basically we want to write 6 over x plus 1 times x minus 1 as some a over x plus 1 plus some b over x minus 1. Then we go ahead and multiply both sides by x plus 1, x minus 1, and we get 6 equals a times x minus 1 plus b times x plus 1. And then what can we say from there? Well, we can form our system of equations. So to save space, I'll just do that up here. So we know there's no x term on the left-hand side, so we can think of that as 0x. And there's ax plus bx, so 0 is equal to a plus b. And the other equation, we know 6 is the constant term on the left, and on the right, we're going to have minus a plus b for our constant terms, meaning our terms without x. Then this is pretty easy to solve. You can actually just add the equations together and get 6 equals 2b. So b has to be 3, and a has to add to b and make 0, so a would have to be negative 3. So now we can go ahead and finish the indefinite integral, because we know our integral of 6 over x plus 1 times x minus 1 dx is really just the integral of minus 3 over x plus 1 dx plus the integral of 3 over x minus 1 dx. And those are easy to evaluate. We just have minus 3 natural log of absolute value of x plus 1 plus 3 natural log absolute value x minus 1 plus a constant. So that's it for part A. Okay, so let's move on to another example. So let's say we have B. We're trying to find the antiderivative of 21x squared over x cubed minus x squared minus 12x dx. The first thing to do here is, again, factor. So we can actually write this as 21x squared over x times x minus 4 times x plus 3. So actually, the equation is a bit redundant. The first time I did this, I actually just left everything in there where you would write it as 3 linear factors, but I suppose it's easier if we just write 21x on top and cancel with one of the x in the denominator and just leave it as x minus 4 times x plus 3. And then this is pretty familiar to the examples we've had so far. So we have 21x over x minus 4 times x plus 3. Should be some, let's say, a over x minus 4 plus b over x plus 3. So then multiply both sides by x minus 4 and x plus 3, and we're left with 21x equals a times x plus 3 and b times x minus 4. So what equations do we get from that? Well, we'll get our x terms are 21, and that's going to equal a plus b. And our constant term is 0 on the left, and that's going to be 3a minus 4b. So this is our system. What happens is we can solve for a. In the second equation, a would then be equal to 4b over 3. So if you plug that into the top equation, you'll end up with 21 equals 7b over 3, which means b is going to be equal to 9, and a would have to equal 12. So that's how we get the partial fraction decomposition. So then our integral becomes just the integral of 12 over x minus 4 plus dx plus the integral of 9 over x plus 3. So this is 12 natural log absolute value x minus 4 plus 9 natural log absolute value x plus 3 plus a constant of integration. I've noticed in the answers sometimes they put these things together if you have the same factor in front of the natural log. I suppose you could, even with them, you could like make 12 the exponent of x minus 4 and 9 the exponent of x plus 3 and then multiply everything together. I would be fine leaving it like this. These are very simple functions, and the integral seems fine. The antiderivative seems fine as an answer, but maybe they would have this as the natural log of x minus 4 raised to the 12th power times x plus 3 to the 9th power plus a constant. I'm not exactly sure, but if you're doing homework on my math lab, it shouldn't matter because I believe that's powered by Mathematica or Maple, so it shouldn't be able to understand that the answers are equivalent. Okay, let's go ahead and do one more. And then if you have any questions, I can go ahead and always do more additional examples. But this one is the integral of x squared plus x plus 2 over x plus 1 times x squared plus 1. So x plus 1 and x squared plus 1 are both prime polynomials, meaning they can't be factored. We have to do the decomposition from here. So basically what we want to do is we want to rewrite x squared plus x plus 2 over x plus 1 times x squared plus 1. We want to write that as two factors. We want to write it as something over x squared plus 1 plus another guy over x plus 1. And the point here is if you have a factor that's quadratic on the bottom, we can't just put a single letter like a on the top. We want to put something on top that is 1 degree smaller. So if you have an irreducible quadratic factor like this, instead of just putting an a on top, we have to put an ax plus a b. And then we can use c on top of the linear factor. So linear factors, you can just put one letter, but if you have the irreducible quadratic factor, you have to put a linear factor on top. So now, again, we want to multiply by the denominator, so we'll have x squared plus x plus 2, and that'll equal ax plus b. The x squared plus 1 will cancel, but we'll still have an x plus 1. And then the x plus 1 will cancel on the second term, but it will be multiplied by x squared plus 1. All right, so now we're going to have three equations we need to take stock of. The first one, we're going to look at the x squared terms. So the only x squared term from the first can come from the ax times the x. So that would be ax squared, so that would be an a. And then in the second term, c times x squared would be giving the only x squared term. Now we'd look at the x terms. So the coefficient of x on the left is 1. What about the coefficient of x from the first term on the right side of the equation? Well, you would have an ax times a 1 from your outside when you FOIL, and a b times x from your inside when you FOIL. So you would get an a plus a b, and then c doesn't get multiplied by any term that has an x, so we don't get a x term from the c times x squared plus 1. All right, then the last, we're looking for constant terms. The only constant term from our first term on the right-hand side, ax plus b times x plus 1, would be coming from your b times 1, so that would be a b, and your constant term from the second group would be your c times 1. So we have these three equations. There's a variety of ways to put them together to solve for the terms. I'll start by, the way I did it was basically I grouped the first two and I subtracted them. So 1 minus 1 would give 0, and then a plus c minus a minus b would just give c minus b. So we have 0 equals c minus b, and then you could add that to 2 equals b plus c, or c plus b. If you add that up, you end up with 2 equals 2c. So that tells us that c is equal to 1. B plus c had to be 2, so b is equal to 1, and that's going to force a to be equal to 0. Okay, so we've got our partial fractions decomposition. You may have done your solved for a, b, and c in some different manner, but as long as you ended up with 1, 1, and 0, then you did everything correct. So that tells us that our integral now just becomes 1 over x squared plus 1 plus dx. I keep forgetting my dx because I'm writing multiple integrals. Dx plus the integral of 1 over x plus 1 dx. So the integral of the 1 over x squared plus 1 is the inverse tangent of x, or the arctangent of x, however you prefer to write it. The inverse tangent of x plus the natural log of the absolute value of x plus 1 plus a constant. And that is it for this example. So the only thing different, you had to include that linear factor, and we ended up solving a 3x3 decomposition to get the partial fraction decomposition, a 3x3 system of equations. Anyway, this is Dr. Lennon signing off. Please let me know if you have any questions.